Welcome to the LBL tool instructional video for VPOP PRO. The LBL tool is a unique VPOP tool that's going to allow you to plan your cranial closing wedge osteotomies and CBLOs and eccentric TPLOs with absolute precision, all to your desired postoperative TPA, postoperative tibial length, and all whilst predicting the tibial mechanical axis shift or induced procurvatum. The tool is based on Paley's defined longitudinal bisector line, and unlike deformity corrections, when we level a tibial plateau, joint orientation line seen here in blue, we're creating a deformity to align a target mechanical axis, seen as purple here, extrapolated from the existing joint orientation line, and we're aligning that with the existing tibial mechanical axis, seen here in green. The realignment to the axes is commonly achieved by a Paley 2 osteotomy of a TPLO, crescentic osteotomy, centered on the articular leveling ACA CORA. In this video, we're going to walk through how to select the LBL tool, how to control and move the LBL tool, how to use the information palette of the LBL tool, seen here on the left, and how to apply a wedge or a crescentic saw tool to the LBL tool in combination. So let's now walk through the basic steps to select, control, and move the LBL tool. The longitudinal bisector line leveling tool can be found in your familiar toolbox in your menu, under crescentic saw. Let's drop that onto our radiograph straight away. And here we have a calibrated radiograph of a sagittal plane projection of a stifle and tibia facing to the left on screen. The LBL tool drops in the center of your screen, occupying the middle 80% of the height of your image, hopefully not too far away from your radiograph that you've typically positioned following calibration. Please note the information palette will only move to the left as far as the image thumbnails will permit, and if you want to have it at the edge of your screen, you'll have to pan it across to the far right. So we have a limit just here. The foundation of the LBL tool is the green preoperative mechanical axis of the tibia, seen as this green line. So let's click the distal end, working from the ground up, to enlarge it to precision mode. Now we're going to pan it to the center, the distal landmark of the center of the talus. So now we progress to the proximal end. Select the tool again. Select the top, the proximal end of the mechanical axis, and we're now going to drag that to the center of the tibial plateau beneath the intercondylar eminences. Now we define our joint orientation line. This is the blue line. We're going to take a best fit tangent to our tibial plateau. I typically take the caudal end here. And once the joint orientation line has been defined, let's take a first look in depth at our information palette for the LBL tool. So here we can instantly see our target mechanical caudal proximal tibial angle, and we can alter it here from the default 85. We can also see our preoperative tibial plateau angle, as determined by the positioning of our first two lines, the green and the blue, mechanical axis and joint orientation line at the tibial plateau. And we can also see our target TPA, our target tibial plateau angle, that's set at the default 5 degrees. And again, we can alter that if we wish. And it has a corresponding effect on our image as well. The default target is 5. The third way we can alter our target tibial plateau angle or target mechanical caudal proximal tibial angle is simply to alter the position of the purple target mechanical axis line that is extrapolated from our joint orientation line that has been selected and positioned by ourselves. So if we click the end of this line, we can gently alter the target mechanical axis. You can see in the information palette, the target TPA is changing accordingly along the target mechanical, caudal, proximal tibial angle. And we can then alter that in the palette as well as on screen. So we'll set it back to our target TPA of 5 degrees here now. A word of caution. As I mentioned before, the foundation of the LBL tool is the mechanical axis, the tibial mechanical axis shown here in green. If you make any alteration at any point during the plan, this will reset your plan back and you will have to reassign the positioning of your joint orientation line. As you can see now, I was to try it and move this. We can pan it and we can reselect it and we can move this proximal end, but now you can see we've lost the best fit tangent and we have to reposition it. So click distally, assign proximally, and then address our joint orientation line. And as before, and as always, we can zoom in for the best assessment of that joint orientation line, like so. So now we move to applying the tool to a cranial closing wedge ostectomy plan. Typically this involves a wedge whose position permits both proximal room for internal fixation holes of a plate, but also one that's not too distal that it induces a marked procurvatum. This typically means our wedge apex is at the distal end of our patient's tibial crest. Now, because we're creating an anatomical deformity to align two mechanical axes, we have options where to choose to site the ACA center of rotation of leveling angulation, or corolla for short. Ideally, we need an isosceles wedge to optimize cortical load share. So we have added that functionality to VPOP for this combination move. We need to be able to plan by CORA methodology to get an accurate postoperative mechanical caudal proximal tibial angle, or TPA. And we also need to ideally know what change in tibial length might occur, and also the degree of induced procurvatum. So using Paley's longitudinal bisector line definition, we can predict what ACA corolla can be used to preserve tibial length. Or indeed, we can slightly increase or reduce tibial length depending on our patient's morphology, such as contralateral limb length, or perhaps there's a notable tibiofibular synostosis where we don't want to place undue distraction on the fibula. Pictorially, if we choose an ACA CORA or leveling CORA, so an ACA corolla, on anywhere on this white longitudinal bisector line, we're going to preserve tibial length. Anything caudal to this longitudinal bisector line, that's a closing leveling ACA, and the tibia is going to be shortened. Anything cranial to this white LBL, and the tibia is going to be lengthened. And all of this information is neatly displayed in your information palette, along with the procurvatum shift. So, to move our wedge, the level is controlled on our target mechanical axis. Thereafter, we can then move it cranially or caudally along the transverse bisector line. And you can see the orange line, which is the resultant shift of the mechanical axis, lengthens and shortens depending on the ACA corolla position. Cranial to the LBL, it lengthens. Caudal to the LBL, it shortens. So ideally we want our wedge apex to be on the LBL, but also close to the caudal aspect of our tibia. And allowing us a wedge of an isosceles shape to optimize our cortical load share. And noting our wedge here, VPOP automatically produces the wedge that correlates with the leveling CORA magnitude as determined by the intersection between the orange and purple lines. And we can just check that here by selecting the LBL tool, and we can see our leveling CORA magnitude is indeed 23.9. All that remains now is to select the wedge, zoom in, get our orientation exactly as we need it. We note our wedge base height. We can note our D3, D1. We create our osteotomy. We define the proximal fragment and click Done. Now we've reduced to 5 degrees TPA or 85 degree mechanical caudal proximal tibial angle. And we've maintained the tibial length because our ACA corolla is on the LBL. You can see here now there's been a minimum change in mechanical axis length, and our corolla magnitude here is 23.9 with only a 4.4 degree mechanical axis shift. Now if we reset that and attempt to plan a CBLO, we can reset that, delete the wedge, and now add in a crescentic saw. We can position our optimum radius and position of the osteotomy. This could be either a 21 blade or an 18 perhaps. Now, when we select the LBL tool, we can now move the ACA corolla, and this will join our crescentic saw tool, like so. So now we can now position anywhere along the target mechanical axis. And then once we're at the correct level, we can address the cranial to caudal position, which will have an effect on the increase and decrease of our tibial length. So let's move this a little further proximally. And now we have an ACA corolla that's just caudal to the LBL. So we are slightly shortening our tibia here. We have a corolla magnitude of 25.3 and a mechanical axis shift of 5.8. There's a subtle mechanical axis delta of a reduction in millimeter length of 1.7 millimeters. But if we note our leveling magnitude of 25.3, we can now reselect our crescentic saw tool, start cutting, define our proximal fragment, and rotate by our corolla magnitude of 25.3. So extending our rotation arm for further accuracy and move to 25.3 here. We can measure our D1 and D3 in the usual manner and template accordingly. Thank you very much.